Welcome to Circuit Valley. I'm Gaurav. This video is going to be the sixth part in the series of video which I have been publishing recently about the usage of protocol decodation and signal decodation and bus decodation using a modern digital oscilloscope. And this video is going to be fifth part. Previous videos we have already decoded SPI, I2C, UART, CAN, LIN, and today in this video we're going to take a look at parallel bus. Parallel bus is pretty basic. There will not be much going on in there. We'll be using our demonstration board which has a FPGA to generate parallel bus signal, and this parallel bus is connected to a DAC, and you can see on your screen all three oscilloscopes are basically measuring parallel bus using a digital channel and measuring an analog output of the DAC. So we have three different classes of instrument to cover the whole range of the operation. On the right side you have RTB2004 300 MHz 2.5 gigasample per second oscilloscope. It supports 16 digital channels. We will use 8 of them to look at the digital channels. And in the middle we have a behemoth of oscilloscope MSOS804A. It also supports 16 digital channel along with the additional clock. We will take a look at its digital output and analog output of both. And on the left side you have MDO3000, MDO3054. It's a 500 MHz 2.5 gigasample per second. It also supports digital channels. So let's take a look at the hardware and we'll see how it goes. You see on this hardware there will be a DAC available, and the parallel bus of the DAC is coming on these bus right here. There's a header, and on this header every single bus is coming. It's of course a digital signal, and we will connect our oscilloscope one by one because we cannot connect all of the oscilloscope at the same time. We'll connect them one by one to this digital or DAC input and the analog DAC output. This board is an oscilloscope demo board. It generates many protocols and various signals. If you want to know more about this board, you can visit my first video in the series. There I describe more in detail what does this board is capable of. So when measuring a digital signal, first of all you must determine what is the level of the digital signal. For that we will use my analog channel, and first I will probe the digital signal. Right now you can see on the screen we are looking at a digital waveform and an analog waveform. This is just to show you as a demonstration. I will take my channel number 2 of this oscilloscope and connect to one of the digital buses. So channel number 2 is on. We'll take this channel number 2 and I'll try to probe the digital bus so that I can know the voltage level, so that I can set the threshold correctly in the logic analyzer. You see, this is my, right now I can disable the channel number 1 and maybe disable the digital channels as well for a second. Okay, so this is my digital bus. You are looking at a web recording of my RTB2004. It's more convenient to record rather than recording a screen. So this is my waveform. Let's do a quick measurement there. And the quick measurement it shows this appears to be a 5 volt logic signal. Okay, so we will set our threshold for the logic analyzer accordingly. If you want, I can take a look at the other signals as well. They are all 5 volt signals. Okay, so let's go in there and disable this channel, enable the DAC output, and enable the digital outputs as well. And we got all 8 bits enabled at the same time. If you want, I can increase the height a bit. Okay, you can see this is flickering a bit. I'll show you one more advanced trigger there. This oscilloscope, to remove this flickering, I can show you HF reject. Okay, and I can also do noise reject if needed. It does basically the same thing. So now you see this sine wave where we are triggering is stable, and DAC input which is going into the DAC, it's also stable. When the DAC input shifts, output also shifts. And let's point out the cursor so that I can show you that how the output is exactly the way it is aligned. You see here all the bits other than D0 is low, so output at its peak it appears to be an inverted output, and here all the bit appears to be high, so output is at lowest. Okay, so this is perfectly aligned, and if you want I can show you a decode and then we can find out. We don't need to do special triggering here because it's perfectly fine with this output trigger. Parallel, it's unclocked, configure D0 to D1, stuff like that. Threshold supposed to be for 5 volts, and you can set it to 2.5 volts. Okay, 2.5, enter. And now let's go back a bit. Protocol we have configured, configuration is correct, and decode. So this is also one pitfall for young users. that you see this oscilloscope shows you two views of the logic. One view which got captured and another view which the bus or bus decoder understand. This helps you to determine that you are not setting the incorrect threshold and stuff like that. Remember, we find out the threshold to be 5 volts and we set in the middle of it, and let's look at it and look at few words, and we are looking at the top window. You can see, and now we are at peak. With the help of cursor I can show you 001 because only the first bit is high, and then 3, then 6, then A, then 10 and stuff like that. Let's look at what is the value when it's at peak. At the lowest, so there is the lowest value in the beginning of the window. You see FF means inverted lowest value. So this oscilloscope can happily decode and decode a parallel bus very easily. Parallel buses are easier to handle. You have two options, clock or without clock. If you have a clock, then you can decode with the clock, but it's very easy to do. So we are done with this oscilloscope. We'll move to my MDO3000. I'll show you the same operation there as well. So we see exactly the same stuff. This oscilloscope appears to be triggering quite stably on the rising edge. Coupling is DC. We can also do HF reject there, so get more stable coupling. And you see the signal is exactly same. Let me show you using cursor. Lowest point of the analog waveform is showing all the bits as FF, and highest point analog waveform is just hexadecimal value of 1. So this output of the DAC is inverted, and we are going to take a look. We'll try to set up a bus decode. Still set to lin. We will set to parallel. Define inputs. Clock data, no. Bus width is only 8 bits. All the bits are correctly set automatically. Threshold we will change. Threshold we will change to maybe 2.5 volts or something like that. This threshold is really important, and we should be able to look at the waveform now. Let's zoom in. You see, at the lowest point, the value is FF. In the analog window, and when the value rises, it shows you different values. Maybe I'll use the cursor itself. So lowest point, FD, FA, F6, E9, F1. Let's look at the highest point. How does the value looks? Highest point, as we showed you, that is an inverted bus, and it shows 1. So this is the DAC input. Digital is DAC input and analog is DAC's output. Exactly what we feed in, exactly what we get out, and the trigger is also absolutely stable on the DAC output, so we don't need to do anything fancy there. So we are done with MDO3000 as well. I'll show you the same operation on MSOS804A. So we have now MSOS804 ready. It appears to be this also have trigger issue, so we will first solve the trigger instability issue with this oscilloscope. Let's go to the trigger menu, setup. We'll do edge trigger, and I want to find out if it does have some kind of qualifier or something like that. Conditioning. It has HF reject or analog noise reject. Noise reject is not doing. HF reject, LF reject, HF reject is the correct option. Okay, so now we see a stable trigger, and you see the analog waveform and digital waveform both on your scope. The value goes lowest and it measures FFF. Value is at the highest, it's 1. Displaying the value of this digital bus. Last time you remember we also used to go to protocol decode. This time you don't have to go to protocol decode, you have to do digital channels and display. First of all you need to define a bus. Bus 1, and supposed to be 8 channels on it. It's already selected, no clock and everything else. And now let's zoom in. So we see the bus is decoded, or the displayed value is available, and you can see already where the value is at highest. Here, right here where the cursor is, it shows FF there, and where is the value lowest, it shows again cursor there. It's supposed to be just 1 or 2 or 3 value. Yeah, so that's correct. So our whole bus is being displayed. If you want, you can trigger on it or do whatever you want, and that's very easy to set up. I think parallel bus was easy. We are done with it. We don't need to do anything at all, and we have till now decoded. So in the series of this video, we have already decoded SPI, I2C, UART, CAN, LIN, and now we have also decoded the parallel bus. This was the 5th video. There are more videos coming soon. Advanced protocols will be now beginning with the MIPI, USB and PCI, and things like Ethernet, Flex, and MIL 1553 is also coming. So keep watching. You can visit my website www.circuitvalley.com.